This video is going to be an example of two-slit interference. So we said two-slit interference worked by doing this kind of a thing where we had a blocker over here, a screen over here. We're going to set our central maximum and we're going to shine light, and because of the light that we shine we're going to get a different maximum and minimum pattern. And we said that the angle from our central point to here was going to be theta. We're going to have a slit separation distance of d, and we're going to have over here a distance to the screen of x, and I want to come up with some numbers. I'm going to say let's find the height of the I equals 2 maximum, and we're going to need some numbers. So this screen is going to be 3 meters away. Our separation distance can be a quarter millimeter, a fifth of a millimeter. We'll do that. We'll go 0.2 millimeters. That's a reasonably typical. We usually go somewhere between 0.1 and 0.5 millimeters. So 0.2 millimeters separation distance, 3 meters away for the screen, and let's get a wavelength of 450 nanometers. I want to find that I equals 2 maximum. So I'm going to say I'm looking for a maximum, so I know that I need my path length difference, which is equal to d sine theta, to be equal to a whole number of wavelengths, and I'm looking for I equals 2, so it equals 2 times the wavelength. If I find sine theta, then I can get there. I know this side is x. If I'm looking for the height y, I know that the tangent of my angle is equal to y over x. So if I can find sine theta, work my way backwards, find theta, I can get there. So I'm going to make theta be my unknown. I know sine theta is going to be equal to 2 lambda over d. So theta is the inverse sine of 2 lambda over d, and I can plug in. I've got a sine inverse of 2 times lambda, which is 450 nanometers. 450 times 10 to the minus 9 meters over the separation distance, which is 0.2 times 10 to the minus 3 meters. I do this and I get an angle of 0.26 degrees. And then I'm going to say I'm looking for y. Y equals x tan theta, so I've got 3 meters times the tangent of 0.26 degrees, and I get 0.0135 or 13.5 millimeters for my height. I do want to point out a couple of things. The sine of 0.26 degrees is about 0.0045. The tangent of this same angle works out to be exactly the same to this many points of precision. I can go 0.0453789, where the sine is really 0.045 0.3784. The point being that for such a small angle, the sine of an angle and the tangent of an angle are really the same for a while, which also means if I'm doing this thing, I can say sine of theta is approximately equal to tangent of theta. So then I could solve this problem because tangent of theta is y over x. I could say y over x is pretty much 2 lambda over d, so y is 2 lambda x over d. And I don't have to worry about inverse trig functions, and I don't have to worry about trig functions. That's going to work out just fine. I can show you though, just in case. So I'm going to get 2 times my wavelength, 450 times 10 to the negative 9 meters, times x over the separation distance, which is 0.2 times 10 to the minus 3 meters. And when I do this, I get actually exactly the same value. So going with this formula is going to be a whole lot faster, just because you don't have to mess around with the inverse sine and whatever. Let's say we wanted to find the height of the first minimum, or the first dark fringe if you like. I'm going to now say that my delta L is going to be still d sine theta, and that's going to be equal to 0 plus a half times lambda. My sine theta, I'm going to say, is about the same as tan theta. Sine theta is about equal to tan theta, equals y over x. So y over x times d equals half lambda. I'm looking for y. Y equals x lambda over 2d is 3 meters, 450 nanometers over 2 times the separation distance, and I get 0.003375 meters, or 3.4 millimeters. That's how I'm going to work this equation.